Welcome to qnawire.
Here we want to calculate the value for E naught, delta G naught, and K for the overall reaction of the balanced half reaction that we have present over here. So remember first of all that the standard potential is going to be an intensive property. So it doesn't take into account the amount of mole that we're going to have. In general, the E0 for a cell is going to be equal to the E0 of reduction of the cathode plus E0 of oxidation for the anode. In this case, what you see is that in both cases we're going to have the reduction. So what we need to do is to flip the second equation in order to get our correct result. So E0 for the cell would be equal to E0 of reduction for the cathode minus E0 of reduction of the anode in this case. So this would become 0.771 volts minus 1.229 volts. Which is going to give us an E0 of minus 0.458 volts. Now, in order to get from here into delta G naught, remember that delta G naught is going to be equal to minus NF, where F is Faraday's constant, times E0 for the cell. In this problem, we need to determine what is going to be the value for N, because it could be confusing from this set of equations, and a lot of people would put directly that the number of electrons that are being exchanged is going to be equal to 2. But as you can see, the actual reaction that we are going to have has a 4 in it. So what we need to do is multiply the first reaction by 4 and the second reaction by 2. So what we're going to get is that 4 times iron 3 plus 4 electrons is going to produce and be in equilibrium with 4 of iron 2 plus. On the other hand, we're going to multiply by 2 and flip the second equation. So we're going to get 2 of water that is going to be in equilibrium with O2 plus 4H plus 4 electrons. As you can see, after we add up both of these equations, the number of electrons, 4, is going to cancel out. And the reaction that we're going to get is the initial balance reaction that was required. 4 of iron 2 plus O2 plus 4H plus. That means that the value for N needs to be equal to 4, as you can see from here. Okay, so now delta G naught would be equal to minus 4 times Faraday's constant, which is going to have a value of 96,000. Let me put over here the value for F, 96,485 joules per volt. Times the E0 for the cell, which is going to be, in our case, minus 0.458 volts. This gives us a value for delta G naught of 176,760.52 joules. Or, which is the same, 176.76 kilojoules per mole of reaction. So 176.76. Oh, actually, the result ask is in joules, so let's plug in directly. 760.52 joules. So that would be it. And finally, to get the value for K, we can relate both of the equations of delta G naught. This is going to be equal to minus RT logarithm of K. At the same time, we know that delta G naught is equal to minus NF E0 for the cell. So we can calculate the equilibrium constant from this value over here. So for us, in this case, I'm going to take advantage of the fact that we have already did the calculation for delta G naught. Actually, no, never mind. We can also remember that the value for RT divided by F at the standard conditions, which means 298 Kelvin, is going to be equal to 0.0592 volts. Okay, so with this information, the E0 for the cell is equal to 0.0592 volts divided by N times the logarithm of the equilibrium constant. Okay, so our equilibrium constant, well, let's take the logarithm of the equilibrium constant would be N times E0 for the cell divided by 0.0592 volts. In this case would be 4 times E0 of the cell, which was minus 0.458 volts divided by 0.0592 volts, giving us minus 30.946. That means that K would be equal to the exponential to the minus 30.946, which is 3.634 times 10 to the minus 14. (3.634) times 10 to the minus 14. So over here is the overall reaction spontaneous as written. No, it is not going to be spontaneous. E0 is negative, delta G is positive, the equilibrium constant is lower than 1. So this is going to be a non-spontaneous process.